Thank you, Mr. Chairman, for your kind introduction. First, I want to thank the organizers to give me the opportunity to present our research here. The title of my talk is Magnetoresistance in Strontium Ferromolybdate, Strontium Molybdate Core Shell Structures. It's a joint contribution from TU Dresden and Academy of Science of Belarus. This is the outline of my talk. I will start with motivation. I will consider the low-field magnetoresistance. I will introduce the fluctuation-induced tunneling model. I will deal with electrical conductivity in the presence of a magnetic field. I will calculate the field and temperature dependencies of the magnetoresistance, and finally some conclusion. The magnetoresistance is a property of a material to change the value of its electrical resistance when an external magnetic field is applied. The magnetoresistive effects in materials are classified into several categories according to their driving mechanism, namely the anisotropic magnetoresistance AMR, first observed by Lord Kelvin in 1857 in nickel and iron. The giant magnetoresistant GMR, a quantum mechanical magnetoresistance effect observed in multilayers composed of alternating ferromagnetic and non-magnetic conductive layers, awarded by the Nobel Prize to Albert Fürth and Peter Grünberg in 2007. The tunneling magnetoresistance TMR, a magnetoresistive effect that occurs in a magnetic tunnel junction consisting of two ferromagnets separated by a thin insulator, and the colossal magnetoresistance CMR, discovered in 1993 property of some materials, mostly manganese-based perovskite oxides, that enables them to dramatically change their electrical resistance in the presence of a magnetic field. The CMR effect in both bulk and thin films always needs a large magnetic field, which limits its application in spintronic devices. On the other hand, the TMR effect is the most sensitive magnetoresistive effect at room temperature. TMR effects as large as 200% can be achieved for junctions manufactured in industrial Canon and ELVA deposition equipment. Theoretically, values up to 1000% were predicted in iron manganese oxide iron structures. TMR sensors cover a resistance from a few ohm to some megaohm. High resistance as well as low resistance sensors might be built by the same design just by changing the barrier thickness. Oxide perovskites with ferromagnetic behavior around room temperature were first reported in the 1950s in the pioneering studies on manganite. The discovery of the low-field magnetoresistance and half-metallicity of strontium ferromolybdates by Kobayashi in 1998 renewed the interest in these materials in the context of their potential application in the field of spin electronics. In the following years, the number of publications replicate the Gardner hype cycle for emerging technologies, an innovation trigger, a peak of inflated expectations, a trough of disillusionment, and a slope of enlightenment. What is still absent is a plateau of productivity. Strontium ferromolybdate double perovskites are good candidates for magnetic electrode materials for room temperature spintronic applications because they present a half metallic character that is a 100% spin polarization theoretically, a high Curie temperature. Note that ferromagnets should be operated in their ordered state below Curie temperature, and the already mentioned low field magnetoresistance. The extrinsic low field resistance in perovskites was discovered by Wang et al. In 1996 in polycrystalline lanthanum strontium manganite ceramics. It was shown that the magnetoresistance in polycrystalline lanthanum strontium manganite ceramics exhibits two distinct regions: large magnetoresistance at low fields dominated by the spin polarized tunneling between the grains, and the high field magnetoresistance obtained also in single crystals. 2 years later, with low field magnetoresistance was obtained by Kobayashi et al. In strontium ferromolybdate. This work describes already the typical resistivity behavior of strontium ferromolybdate, a semiconductor-like behavior at low temperatures, followed by an upturn to a metallic behavior at high temperatures. 3 models are applied for the description of magnetoresistance. The empirical exponential model is simply a good approximation of the experimental results, both for sintered and granular strontium ferromolybdate ceramic samples. The tunneling model, developed for barium strontium ferromolybdate, considers the conductivity due to elastic tunneling occurring through a barrier between two non-interacting grains, possessing equal spin polarization P but different directions in the neighboring grains, under an external magnetic field H. Since the average cosinus of the angle between the magnetization directions of two neighboring grains yields the squared reduced magnetization m squared, the resulting magnetoconductivity equals m squared times p squared, equation 1. On the other hand, the grain surface is a defective double perovskite, whereof the geometry, vacancies, and anti-side disorder acts as random spin pinning centers, which suppress ferromagnetism. Therefore, the bulk reduced magnetization is replaced by a magnetic field dependent magnetization m sub Gb of the region close to the grain boundary, which was taken in the functional form widely used for spin classes possessing a weak anisotropy, equation 2. Rewriting the first equation in terms of magnetoresistivity, we arrive at equation 3. Intragrain magnetoresistance is accounted by adding a linear term, equation 4. This linear term is typical large near the magnetic ordering temperature. In the limit of small fields compared to the magnetic field parameter H sub 0, the empirical model coincides with the tunneling one. To improve the fit of the magnetoresistance data of pressed barium strontium ferromolybdate powders at low fields, a hyperbolic tangent function correction was added later. The random mean square noise voltage generated in an RC circuit on an ideal capacitor is given by kT divided by the capacity. Therefore, large voltage fluctuations occur when the capacitance of an intergrain junction is small. For a dielectric constant of 40, a barrier thickness of 1 nanometer, and a contact area of 300 nanometers square, the junction capacitance is in the order of 0.1 femtofarad. For fluctuations to occur, the electrostatic energy per electron should be much larger than the thermal one. In our example, the ratio of both is in the order of 0.1. The fluctuation-induced tunneling model describes conducting grains separated by energy barriers subjected to large thermal fluctuations. The tunneling occurs between large metallic grains across insulating barriers with a width W and an area A. It is specified by two parameters: the temperature T1, characterizing the electrostatic energy of a parabolic potential barrier, equation 1, where K is a Boltzmann constant and the characteristic field E sub 0 is determined by the barrier height V sub 0, equation 2, the temperature T sub 0 representing T sub 1 divided by the tunneling constant, equation 3, with a reciprocal localization length of the wave function G, equation 4, where m sub e is the electron mass and stroked h is a reduced Planck constant. The resulting inverse modal resistivity is then given by equation 5. The fit model was recently applied to intergrain tunneling in polycrystalline strontium chrome molybdate and strontium ferromolybdate ceramics, as well as other half metallic double perovskites containing iron or chrome at one p side, or rhenium or tungsten on the other. In the low voltage regime, supposing direct tunneling through thin enough barriers, the sheet resistance of a granular nano-sized strontium ferromolybdate strontium molybdate core shell structure up to a factor of F is given by equation 1, where E is an electron charge. The factor F depends on the ratio of the reciprocal localization length phi and the wave vector of the wave function of the tunneling spin down electrons key down, as well as on the angle phi between the magnetic moments of the neighboring grains. In nano-sized granular strontium ferromolybdate strontium molybdate core shell structures, the barrier thickness is in the order of the localization length of the wave function. On the other hand, the barrier is much thinner than the magnetic length equation 3. In this case, the barrier height was experimentally found to follow relation 4. The coefficient beta was attributed to Zeeman splitting amounting to about 1 Bohr magnetron for magnetic field perpendicular to the current and to about 20 Bohr magnetron for magnetic field applied parallel to the current. The coefficient gamma was adapted from data of a magnetic sensor based on a tunneling device comprising a 2 nanometer thick double perovskite lanthanum cobaltite magnetite layer grown on top of a niobium doped strontium titanate substrate and capped with a thin platinum layer. A theoretical estimate of gamma yields a slightly higher value, since we are not dealing with collision-free electrons. Now The resistivity of strontium ferromolybdate was calculated independent on the temperature T and the magnetic flux density B. The parameters used for calculation are compiled in this table. The figure shows also a comparison with a zero field resistivity with our recent measurements on nano-size granular strontium ferromolybdate, strontium molybdate samples. The magnetoresistance is defined as a resistance change when applying a magnetic field relative to the field-free value. This figure illustrates the magnetic flux density dependence of the magnetoresistance MR. The obtained negative values are similar to the ones obtained for high-temperature sintered strontium ferromolybdate ceramics. The predicted absolute values increase with increasing magnetic flux density. The decrease at very high magnetic fields is an artifact of the model attributed to the termination of the series expansion of the field dependence of the tunneling barrier. The location of the minimum of the model depends on the value of the parameter gamma. With increased gamma, it shifts to lower fields. The predicted temperature dependence of the magnetoresistance in nano-size granular strontium ferromolybdate, strontium molybdate core shell structures is much weaker than in strontium ferromolybdate ceramics. With weak temperature dependence is a consequence of the parameter T sub 0 in the order of the temperature at resistivity measurements. The increase of the absolute values up to a temperature of 50 Kelvin, following by a further decrease, is in accordance with experimental data for granular strontium ferromolybdate samples which were related to the fluctuation-induced tunneling model. The calculation confirms that contrary to manganite and strontium ferromolybdate ceramics, the magnetoresistance of nano-sized strontium ferromolybdate, strontium molybdate core shell structures is only weakly temperature dependent. This would be an advantage for device application near room temperature. The calculations are in qualitative agreement with experimental results of sintered granular strontium ferromolybdate obeying the fluctuation-induced tunneling model. These are my conclusions and the sponsor of this work. Thank you for your time and attention.